Welcome back everyone, Patrick here. Moving on to the next question dealing with maximum and minimum word problems. So we're told that a string that is 32 centimeters long is to be made into a rectangle, and we have to find the dimensions of the rectangle that would give us a maximum area with that constraint of the string being 32 centimeters. So what's happening, we're taking a string that is 32 centimeters and we are making it into a rectangle. So what else does that mean? It means that the perimeter of this rectangle is going to be 32 centimeters, right? This string, this full string here is 32 centimeters and we make it into a rectangle, it means the perimeter of the rectangle is going to be 32 centimeters. And so what we got to do is find out what dimensions of this perimeter being 32 centimeters would give us the maximum area, because notice that there's different combinations. So like if we say maybe that the length is 10 centimeters, that means 10 is 20, we have 12 left for a perimeter of 32, that means that the width would have to be 6. And so what would the area be? In this particular case, it would be 60 centimeters squared. So that's one combination. What if maybe we had like 12 over here? So we'd have 12, that would give us 24. That would mean that this would have to be 4 and 4, right? 12 plus 12 plus 4 plus 4 would give us 32 centimeters as well. But notice that the area in this particular case would be 12 times 4, which is 48 centimeters squared. Right? So there's different combinations for the length and width, and those are going to give us different areas. And so what we're trying to find is what is the combination that would give us the maximum possible area. And so what we want to do is we want to generalize this, and let's bring in some variables. So I'm going to let's let the length be x, let's let the width be y. So let's actually write this. X is going to be the length of the rectangle, and then y is going to be the width. You could use any variables you want. If you want to use L for length, W for width, I'll just keep it as x and y. And with that labeling, we know this is x, this is going to be y. What do we know? We know that x plus x, which is 2x, and then y plus y, which is 2y, we know that that has to equal 32. The perimeter has to be 32. And so this here, it's called our constraint. And then what we're trying to maximize is we're trying to maximize the area. And the area of this rectangle would be length times width. So in this case, it would be x times y. Now, what's the problem here? Well, the problem is that we're dealing with two variables. And if we want to try to find the maximum of something, of an equation, it has to be in terms of one variable. So we have to make the area in terms of either x or in terms of y. Either or works, and what we could do is we could use the constraint that we have to isolate for x or y and then plug it into the max-min function that we're working with. So let's simplify this a bit. Notice that everything can be divided by 2, so that's the first simplification we could do. So we'll have x plus y equals 16. And then whether you want to make this in terms of x or y, I'm going to make it in terms of x. So what I'll do is I'll isolate for the y here, bring the x over, so we'll have y equals 16 minus x like that. And then we'll plug in this expression, 16 minus x, for that y right there. So we'd end up with A equaling the area equaling x times 16 minus x like that. And then notice that this here, it's actually a quadratic that we're dealing with. And when we distribute, we'd end up with this, negative x squared plus 16x, like that. So that is the area that we would get depending on the length we're going to use for the rectangle. So if we're going to use a length of, let's say, 10, for example, we'd plug in, notice how it works. So if we have 10, remember we had 10, 10, and then we had 6 and 6. So that gave us an area of 60 centimeters squared. Well, notice what happens when we plug in 10 here. We'll have 10 to the power 2, which is 100, times negative 1, negative 100, plus 16 times 10, which is 160, negative 100 plus 160 would indeed give us an area of 60 centimeters squared. But what's nice now is that we generalize this, and now it's in terms of a variable. We're not just dealing with a specific case. So what we can do, let me actually write out this area, quadratic right here, is we can find when is the area going to be a maximum. And notice that we can get that by completing the square on this, changing this quadratic, because it's in standard form here, to vertex form. And notice that it is going to give us a maximum because the coefficient, leading coefficient, is negative here, this negative 1, meaning it's a parabola that opens down, meaning the vertex we're going to get is going to be a max point. So let's complete the square on this. So what we can do is we can first factor out a negative 1 from both of these. So we'd end up with x squared minus 16x, like that. Close the bracket. There's no c value in this case, so we just leave that blank. And then what we do is we take that negative 16 divided by 2 and then squared. So that would give us negative 8 to the power 2, which would give us 64. So then we'd end up with negative x squared minus 16x plus 64 minus 64, like that. Then we take the negative 64 out. When we take it out, we got to multiply it by what's in front. Got to multiply by the negative 1, so that would give us positive 64. And then remember that this here is always going to be a perfect square trinomial. And we're left with that right there. So let me write this over here. We took this area that was in standard form and then changed it to vertex form. Like that, right? Both of these are the same thing. If you graph both of those, you'd end up getting the same graph. And what's nice now is we can get the vertex. And notice that the vertex is positive 8 and 64. And what does that mean? Well, notice that the x value is 8. So that's the length. So we end up with 8 centimeters here. And notice that because it's in terms of a, that means this y variable. Not this y variable, but sorry, maybe I shouldn't say y. The dependent variable in this case is the a, which would give us the area right there. And so that ends up being the answer. So basically a length of 8 centimeters, 8 centimeters, 8 centimeters. Notice then we could solve for the width. We can just plug in that 8 over here. 16 minus 8 would give us a width of 8 right here. And that makes sense because if you add these up, you'd get that perimeter of 32. And then notice that when we multiply the length and the width, what do we get? We get 64 centimeters squared, which is exactly what we got with the vertex here. So when x is 8, the area is 64. And then also, they want the full dimension, so the y value, as I just mentioned, would be 16 minus that x value of 8, so the y value is 8 as well, right? So 8 centimeters like that. So what dimensions of the rectangle would give us a maximum area? The dimensions would be 8 centimeters by 8 centimeters. And then the maximum area would be 64 centimeters squared. All right, so if you tried other combinations, I tried a couple at the beginning, whatever combination with this perimeter of 32, it's going to give you a lower area than 64. 64 centimeters squared is the maximum area that you can get, and those are the dimensions that give you that.